All right, guys. So as we were saying before the interruption from the Zoom, so I was saying that we need to first think of the plus sign as meaning together with, and the equal sign means is equivalent to. And ensure to look at the component vectors to see whether or not the nose of one vector is going into the tail of the other vector, right? And as I was saying, we'll see how to treat with these when we're doing an example. We have several examples that we can look at. All right, so moving along. Now we're going to be looking now how to add vectors. Now, when we're adding vectors, vectors can be added based on whether or not we have them on a graph where we're actually using coordinates, or we have them freely just drawn as line segments on a paper where we're using letters to represent their magnitude. And in the case where we're just calling a vector by a letter or so on, we're treating these letters as unknown. So when we're treating vectors in this way, we're really treating them in an algebraic way, all right? When we're adding them with the coordinates on the graph, we're actually adding actual values of the vectors. But when we are dealing with just letters and symbols in terms of their magnitude, we are just doing vector algebra. Is that clear, guys? All right, so we'll see how it works when we look at after we are through with the algebraic aspect of vectors, then we look at the graphical view where we're looking at position vectors. All right, we say when we're adding vectors, as I said before, the plus sign does not mean to sum in the arithmetic sense. And the equal sign does not mean equal in the arithmetic sense. So what do we really mean when we're adding vectors? When we're adding vectors, what we're saying is that if we use the triangle and the parallelogram laws, now if we look at these laws, we can use the same laws to add vectors. Now, what does the triangle law state? So let us look firstly at the triangle law and then the parallelogram law. So the triangle law states that the resultant of any two vectors is equal to the length and direction of the line needed to complete the triangle. All right, so all that is saying, these two vectors that we have here, the vector A and the vector B, right? Remember we were talking about nose to tail earlier, right? So if we are to arrange these two vectors so that the nose of one vector go into the tail of the other. So this is the nose of the vector A, and we want to arrange it that nose going to the tail of the vector B. But remember now, we cannot change the direction of how these vectors are, where they are going. But what we can do, you remember when we're doing translation, we can slide them and keep them in the same orientation. So if you move this and slide this up to this point, if you slide it up to here, then it would look like this. Everybody see that? Everybody see what I'm talking about, guys? You take the tail of the vector B and you align it with the nose of the vector A. Is that clear, guys? Raise your hand if you understand what I'm saying. Now, don't look at this diagram in its entirety. entirety yet. We are saying that these are two component vectors, and we want to add them based on the triangle law. But before we can add them, we have to arrange them so that the nose of one goes into the tail of the other. So we would actually physically move this one, put it over here in the same direction where it was. So this now would be the vector B. So you notice that it still have the same direction as this one over here. So you just displace it and put it right at the nose there. Now, once you have done that displacement and put it there, the next thing that we have to do now is to complete this into a triangle. Now, to complete this into a triangle, we will have to draw a line from the beginning of A to the end of B. So we would have to draw a line like that. Now, this line that we have drawn would be the line that completes the triangle. And this line is the resultant vector line. Or this line segment going to be the resultant vector. Now, to distinguish the resultant vector line different from the components lines, we generally put two arrows on the resultant vector. So this would be, if this is the point where the vector ends, and let's say that the vector ends at C, if this is the point C, and this is the point A, then this vector would be the vector AC. So this vector going from A to C would be the vector AC. But notice that it starts at A, it ends at C. The components also start at A, they start at A and they end at C. So the components and the resultant, they're starting at the same point and they're ending at the same point. So we can say that they are equivalent vectors. And so to write them to show that they are equivalent, we are just going to say the vector AC is equivalent to, because this equal sign means equivalent to, the vector A, and in this case, if we want to say the vector AB, so to equivalent to the vector AB together with, the plus sign means together with, the vector BC. And that's how we write when we are adding vectors. So this is how we add vectors, right? Now, to leave it like this is okay. If you are given a common letter or some letter for each of these lines, then you can put the letter that you get for those. So if this is A, you put A down here. For that line, if that line is labeled common A, you put common A there. This line is labeled common B, you put common B there. But first you write it like this, then you put the common letter below like that. Is that clear, guys? Let me see your hands if you're understanding. All right, Miss Green is okay. Miss Cabrera, all right. Miss Doherty, you're following? All right, good guys. All right, now we say that we can also add vectors using the parallelogram law. Now, the parallelogram law is useful when the two vectors that we're adding, they start at the same point. So you notice these two component vectors here, both of them starts, call this point O. Both of them start at O. And they're going out like that. If you had looked at the previous scenario, what we would have done, we would have relocated one vector so that the nose of one going into the tail of the other. That is when we're doing the triangle law. But if we're doing the parallelogram law, what we do, these two lines, the line from O to B and the line from O to A, we just draw a line parallel up here. In other words, we complete it into a parallelogram. So this line, we will draw another line parallel to that line up here. And for this line, we draw this line parallel over here, right? So the length of this line and the length of this line would be the same, right? The length of this line and the length of this line would be the same. Is that clear, guys? Now, once we have completed the parallelogram, once we have completed and drawn the parallelogram, the resultant vector now would be the middle line that starts the same place where the other two vectors start and ends at the point at which the parallelogram would end with when you add the other two lines, dotted lines. Is that clear, guys? Now, just in a similar way, if you take 1/2 of the parallelogram, if you're taking this line going this way, remember this line, this dotted line would be parallel to this line. They would have the same magnitude and the same direction. So it means that this vector would be the same as the vector B. Do you agree, guys? You agree with what I'm saying? Because two vectors are equal if they have the same magnitude and the same direction. These have the same exact length. And they are going in the same exact direction. So it means that this side would be the same as from O to B. And so if you're thinking in terms of now the components, so you could go this way. You can start from O going to A, and from A going into B, right? So it means that the components then would be these two. And so you would add the two components to get the resultant. So you would add A plus B to give you the resultant. Is that clear, guys? Guys, is that clear? Raise your hand. Ms. Cabrera?
Yes, that's clear.
Ms. Green?
Yes, sir.
All right. So this is a parallelogram law. So if you get two vectors that start at the same point, you form them into a parallelogram. And then you draw this line in the middle. Then you add the two components to give you the magnitude of the resultant. All right, guys. All right, now this is two examples of one of the parallelogram and one of the triangle law, right? Now, if you notice, when you're looking at this scenario, so if we are given this scenario where these two vectors, which would be the force one going up, force two coming going this way, but these two forces start at the same point. Now this one would work very well with the parallelogram law. All you need to do is draw another parallel line. Draw another parallel line to this. Oops. I guess I should probably use a line. Draw a parallel line to this vector here. So you draw a line the same length of this, and it is parallel to that. And to this vector now, we will draw another line from here to here, which is parallel to that. All right, and that would be, this line supposed to be parallel to this line. And then the resultant now, you would draw the resultant from here, going straight through to the point where those two lines meet there. And then now, to get the value of the resultant, you're just going to simply do what? You're going to add F1 plus F2. So this resultant would be equal to F1 plus F2. You get the idea, guys? And this is what the F3 represents. The F3 represents F1 plus F2. All right. Now, if their components is already arranged in this way, nose to tail, then this one you can use a triangle law. So all you need to do is start at where the tail is for the two components, and you move up to where the nose is at the last component. And so now this now becomes the resultant vector. Is that clear, guys? And so that would represent, sorry, oops. That would represent this scenario. All right. Now this resultant would also be F1 plus F2. So in other words, what we are saying is F3 is equal to F1 plus F2. Is that clear, guys? Guys? All right. So this is an example of when would you use the parallelogram law? If the two components are tail to tail and they're starting at the same point, you form that into a parallelogram. If you have a nose to tail situation, you just form that into a triangle. All right, guys, I hope everybody is following and understanding. All right, moving along. So here now we have a scenario where we have these two components. They're starting tail to tail. So we could draw this into a parallelogram and use a parallelogram rule. So if we're going to use the parallelogram rule, we'd have to draw another line parallel to this one here. That's to be parallel to B. And then you draw another line from here, which is parallel to A. And then now you would draw the resultant through the middle here. All right? Now, so that is if we decided that we are using the parallelogram law. But remember too that we could also use the triangle law. But in order to use the triangle law, what we would have to do, we would have to arrange these two vectors so that the nose of one going to the tail of the other. So what we would have to do exactly is to either take this vector, slide it down all the way down to here so that this tail will be at the nose here and have it looking like that. So this would slide down the vector A down to this point. You slide it down to the end here so that the nose of this going into the tail of A. So that means A would be right here now, right? The following, guys? And once you slide it down so that A is there, then all you have to do now is form that into a triangle starting at the tail of B and you end it at the nodes of A. And this now becomes the resultant. And so that is what happened. That is what happened in this scenario here. So this is what they did to get this into the triangle form. So if you're using the triangle law, this is how you would work it. Using the parallelogram law, you would draw two parallel lines to A and B. Is that clear, guys? Raise your hand again so that I see that you're understanding. All right, good. So here now, we're going to be looking at some questions in relation to vectors. All right, so for question 1 here, and in this case, what we're really doing is vector algebra. Notice that we are not working on any graph paper. So these are vector algebra. So it says that the parallelogram PQR is a parallelogram, and you have to find the following. So you are to find what PR is, and when they say find PR, they are referring in relation to what the letters that they give you here. So they give you this letter A, and they give you this letter B. So they said find PR. What they mean is to find PR in terms of what? A and B. That's what they are saying. In terms of A and B. Meaning that you have to ensure that when you find PR, you are representing it in relation to this A and to this B. Now, if you are to find PR, then you would have to start at P, a line starting at P, going right to R. So the line PR here would start at P, and it would go all the way to R. So that's PR. Now, in terms of the letter A and B, we have to now treat PR as a resultant vector. All right, then how do we calculate the in terms of A and B? This is how we have to calculate it. Now, we know that in order to go from P to R, which other direction could we go to get to R apart from that straight line? Escavera, which other path could we travel? Which other components could we use to get to the point R? Which other lines could we put together to and could we follow to get to R? Which direction? Which other direction?
Sir,
so we could take this route. We could go from P to Q, and then from Q to R. That would get us to the same endpoint, right? Right?
I was going to say from B to S, then to S to R.
No, we don't. Remember now, we're not starting at B. Where about the resultant start, that's where we start. So if we are saying, don't treat this as a starting point. This is the actual magnitude of PQ. A is the magnitude of PQ, and B is the magnitude of PS. So when we're talking about the line segment, you start with the vertices letters, the capital letters you're working with, right? Don't pay any attention to the comma letters. So in terms of direction, we can go from P directly to R, or we could take the route going from P to Q and then from Q to R. That's one direction. We could also go from P to S and then from S to R. Now, it really doesn't matter which of them you want to use. But when you get to R, you want to show that PQ in relation to A and B would have some relationship. All right, so I'm going to show you both ways. So suppose we write PQ, the vector PQ would be equivalent to, not PQ, I want to say, the vector PR, this is the resultant vector that we're really writing first. So the vector PR is equivalent to the vector PQ plus the vector QR, right? Meaning that we can, instead of going directly from P to R, we could go from P to Q and then Q to R, all right? But what, in terms of A and B now, what is the length of PQ? The length of PQ would be what? Would be A. So PQ would be A. Then now in terms of A and B, QR would be equal to what?
B.
Yes, QR would be equal to B since QR is parallel to B and have the same length. You understand? So this would also be equal to B. So QR would be B. So it means that PR would be equal to A plus B. That is if we are using this direction. If we go the other way, from P to S and then P to R. So we would have PR equal PS plus SR. All right, what we know now, PS would be equal to what? In terms of magnitude, that would be equal to B. And SR would be parallel to A, so SR would be equal to A. So it would be B plus A, which it doesn't matter the order that you write it in, that means the vector addition obeys commutative property. So it is the same as A plus B. So you see, whichever way you look at it, you will get the same answer. Is that clear? Guys?
Yes, sir.
Miss Green, is it clear?
Yes, sir.
Miss Dorothy, is it clear?
Yes, sir.
All right, now, so we are going to be looking at the others in the same way. So we want to look at from Q to S. So whichever one they ask you to find, you're going to treat that one as a resultant vector. So start with QS as the resultant vector. And then now you choose other pathway that you can go from Q to S. All right. So if you start at Q and you go to S, then this line would be the resultant vector from Q to S. Which other way you could start from Q and reach S?
QR plus RS.
Right, so you can go from Q to R and then from R to S. Now, when you're doing the pathway, make sure you put an arrow based on the direction you're going. You're going from Q to R and then R to S. All right, so QS is equal to QR plus RS. Now, would RS be equal to A?
Yes, sir.
Look carefully, you know. Would RS be equal to A? Notice A has an arrow going that way, but RS has the arrow coming in the opposite way. You follow? So remember, if two vectors are going in the opposite direction and they have the same magnitude, then they are inverse to each other, right? You follow? So from Q to R would be equal to B because this is going in the same direction as B. So this will be equal to B. But from R to S would be equal to minus A because it is going opposite to A. Do you see that, guys?
Yes, sir.
Miss Green, do you see that?
Yes, sir.
Miss Cabrera,
Yes, sir.
you understand, right? So if they define A, you have to look at the arrow of A, and any direction going opposite to A, you have to put a minus, right? All right. So now, you could work, if you were working it the other way, from Q to P, and then from P to S, it should give you the same answer as this, right? Because whichever way you're going, you're supposed to get the same answer. So you can say QS is equal to QP plus PS. Now, if we go from Q to P, then we are going in the opposite direction of A. So this becomes minus A. But from P to S would be going in the same direction as B. So that would be plus B. And so this would be the same as B minus A. You see that, guys? Guys?
Yes,
Yes,
sir.
sir.
All right. Now I'm going to ask you now to try C. Let me see how well you are thinking. All right. So I'm going to clear what I have here, and I'll give you a chance to try this one. And try C and then try D. When you're finished, raise your hand, guys. All right. Anybody get the answer to this one yet? Raise your hand, let me see. All right. Let me help you through this one, guys, so that you see what is happening. So this is saying that you're to find QX, where X is the midpoint of QS. If X is the midpoint of QS, that means halfway between Q and S, in the middle there, in that midpoint there, you would have X. All right. Now, what do we know? We know that QS is equal to QP plus PS. In terms of A and B, that would be equal to minus A minus A, sorry, can't write